A high-performance athlete relies on skeletal muscle cells, or myocytes, to generate movement. To keep up with demand, these cells hold massive glycogen stores and are highly adaptable, shifting instantly between aerobic and anaerobic metabolism to power the body. But myocytes have a critical vulnerability. They maintain an absolute continuous dependence on ATP, adenosine triphosphate, the primary energy molecule of the cell. The cell needs ATP to flex, but it also strictly requires it to relax that contraction and to keep its outer membrane intact. Looking at this diagram, destruction begins at step 1, the initial insult. Triggers like crush trauma, ischemia, toxins, or exertion cause oxygen demand to outpace supply. The main energy engine, oxidative phosphorylation, halts. Glycolysis ramps up, causing lactate and acid to spike. A large-scale physical trauma on the outside of the body instantly translates into a microscopic energy crisis on the inside. The muscle cell is now completely unpowered. Moving into step 3, the lack of ATP immediately halts the cell's essential maintenance systems. The most vital of these is the sodium-potassium ATPase pump, a protein structure on the cell membrane responsible for keeping dangerous ions out. This animation shows the immediate osmotic chain reaction. With the pump broken, sodium accumulates inside the cell while potassium leaks out. Because water naturally follows sodium, it rushes directly into the intracellular space. The physical manifestation of this chemical shift is severe swelling. Immense osmotic pressure builds, forcing the myocyte to dangerously balloon outward. The cell is effectively drowning in its own fluids, pushing its structural limits and guaranteeing a catastrophic failure if the pressure isn't relieved. Returning to the diagram for step 4, the internal machinery begins to fail. The sarcoplasmic reticulum, or SR, normally stores calcium. But as its transport protein, SERCA, slows down, calcium is trapped floating in the main fluid of the cell, the cytosol. This elevated calcium has 2 devastating effects. First, it locks the muscle into a sustained, unyielding contracture. Second, it activates proteases and phospholipases. These are destructive enzymes that act like chemical scissors, physically cutting the cell's internal myofibrils and directly injuring the mitochondria. In step 5, the collapsing mitochondria and arriving immune cells flood the immediate area with reactive oxygen species, or ROS. These are highly unstable molecules like superoxide, hydrogen peroxide, and hydroxyl radicals. These unstable molecules attack the cell's fats in a destructive process called lipid peroxidation. This dissolves the outer membrane and further cripples any remaining functional ion channels. At this stage, the cell has passed the point of no return. Its own energy centers and biological machinery are actively dissolving its structural integrity. Step 6 delivers the breaking point. As hydrogen ions continue to rise, the internal pH drops into a state of severe acidosis, completely ruining the function of survival enzymes. Unable to withstand the internal swelling and the acid degradation, the bloated myocyte membrane finally violently rips open. This diagram shows the exact contents of that breached vault spilling into the extracellular space. Myoglobin, creatine kinase, or CK, massive amounts of potassium, and phosphate all leak out. What was absolutely necessary for life inside the cell is highly toxic outside of it. A localized tissue rupture now becomes a lethal systemic threat to the entire body. The body detects the chemical spill and initiates step 7, inflammation. A flood of cytokines responds to the area. Interleukin-1 and interleukin-8 recruit destructive white blood cells called neutrophils, while tumor necrosis factor alpha actively promotes further protein breakdown and programmed cell death. In step 8, the body mounts a desperate systemic rescue. It increases sympathetic nerve drive to support falling blood pressure, ramps up respiratory rate to blow off the severe acidosis, and activates satellite cells, which are local muscle stem cells, to attempt tissue regeneration. But the volume of debris is too great. This chart tracks the dense myoglobin protein as it travels from the destroyed muscle tissue, circulates through the bloodstream, and enters the delicate filtration tubes of the renal system. This massive surge of myoglobin violently clogs the kidneys, causing acute kidney injury, or AKI. This specific renal failure is the hallmark clinical sign of rhabdomyolysis. Despite aggressive attempts to regulate blood pressure and clear the acid, the body's repair mechanisms are completely overwhelmed by the sheer volume of toxic debris entering the systemic circulation. The most immediate threat on our diagram's special pearl node is a massive extracellular dump of potassium from destroyed muscle fibers. This severe spike, called hyperkalemia, reaches the heart and directly interferes with the electrical system, causing profound weakness, slowed conduction, and highly fatal arrhythmias. Returning to the site of the original injury for step 10, the final fate of the cells depends entirely on the scale of the trauma. A mild injury results in low ATP and poor calcium cycling, leading to simple, reversible muscle fatigue. A moderate trauma forces the cells into apoptosis, controlled death, followed by repair. But severe injuries dictate a completely different reality: irreversible cellular necrosis, rhabdomyolysis, and permanent scarring known as fibrosis. A physical crush injury isolates the muscle tissue from its blood supply. By severing that local energy line, the impact triggers a biochemical self-destruct sequence that, without medical intervention, will systematically shut down the human body.